Sir, very good afternoon, sir.
Hello. Yes. Good afternoon. Yes.
Good afternoon, sir.
So, Professor Pavel has joined or not yet? Okay. Yeah. So now we have keynote lecture of Professor Pavel Petro, na?
Yes, sir.
Okay. Fine. So we are waiting for this. Yes.
Yes.
Okay. Yeah, maybe Pavel Petro. Acha, he joined as attendee. You have to make him panelist actually. Yeah.
Okay, sir.
Yes. Yeah. He joined as attendee. Yes. This is what it is. Pavel. Nishka. Pavel. Here. Yes. Still they're coming one by one. Maybe only.
Sir, Pavel, sir, can you hear me? Hello, sir. Pavel, sir. Sir, whether we are audible, sir?
Hello.
Hello, sir.
Good afternoon,
Sir,
colleagues.
very good afternoon, sir.
Yeah. I didn't understand how to switch on my microphone, but now if you hear me, it's okay.
Sir, I think we can't change you as a panelist.
Okay.
You just exit from this meet and join once again, sir. So again, I sent the WhatsApp also, sir, the link. Whatever we sent yesterday, the same link I WhatsApp to you, sir. But you can join that link, sir.
Okay. Could I switch on my presentation? Could I switch on my presentation now?
That's why we are saying, sir, please come out from the meeting and join once again, sir.
Okay.
We are unable to make you as a panelist or a presenter.
Okay.
So please join once again. You come out from this meet now.
Yeah, that means you log out and again log in.
Yes, sir.
Yeah. Log out and then again log in. Yes.
Yes, sir.
Yeah, I think he has left now. Now he has. Professor Petro, you first quit and then again join.
Yes, sir.
Yeah. He's there, no? I think now he has left. He will again join. What attendees have to come here? From your side, it is coming. Webex event is locked. Okay. Yeah, I don't know that. Professor Pavel. Okay, I just send the message. Okay. You also check the permission, etc. Ramesh Babu, because he displayed his screen. It seems it shows the Webex event is locked. Some locking or something, I don't know. Even I am not able to see. Okay, many attendees also. Is there some problem?
Okay. Ask him to join using another email account, sir.
Another email account.
Yes, sir.
Okay. Which account? Which account he should join?
Any account, sir. Any account, another account.
Another account means another email. That you mean to say that?
Yes, another email.
That whether he.
For that.
Now he joined through this one. No, he joined actually. You just see that. See, now he's shown in the attendee again. I think he's becoming an attendee only. He's becoming attendee only because
Yes,
in
sir,
the
he came, sir. He came.
Make him panelist.
Make him panelist actually. Can we make?
Yes, sir. Yes, sir.
From here? Yeah. Now he has it.
Yes, sir. Yes, sir. Sir, now you can mute, sir. Unmute, sir.
Good. Yes.
Make him presenter.
Now we should unmute that. Okay, we can unmute. From here also we can. Yeah.
Yeah. Good afternoon, colleagues. Once again, it seems that it works.
Yes. You are audible, Professor Pavel.
Yeah.
We can listen to you. Okay. Yeah. Only thing, video maybe you can switch on. So if your camera is working, we can see your face.
Okay, just a moment.
Okay. Yes. Okay, great.
Hello, everyone.
Yeah. Thanks. Yes.
Okay.
Yes. So maybe before you start, Ramesh Babu, I am introducing the speaker first. Huh? Okay. Yeah. So, friends, okay. Dear colleagues, we are very happy to have our first keynote lecture by Dr. Pavel A. Petrov, who is at present head of the department Materials Processing by Pressure and Additive Technologies, Moscow Polytechnic University, Russia. And he will be speaking today mostly on the material flow during the closed die forging by numerical simulation, how numerical simulation helps in making good quality product. So Dr. Pavlov's research interest include technological process design, computation modeling of the process, material modeling of computation modeling, additive manufacturing, and he has published over 50 good research papers, and some of them are in Russian journals and some are in English journals, and he has knowledge. He works in the materials area as well as manufacturing, and he visited in fact India at IIT Guwahati. Also he gave a GAN course on near net shape manufacturing of the from aluminum products. Okay, and then at the same time he is also doing one Indo-Russian project in which I am with him together, and he is very active, and he takes whenever that we have discussion, or if I draft a paper, he will carefully read it and offer suggestions. Similarly, whenever he writes a paper, he just takes the suggestion. So he is a very active partner and open to collaboration. So that's why anybody who is interested to collaborate from India, I think he will help actually, and he will be willing to join. So with this brief introduction, I now invite Professor Pavel to tell about, maybe he can take about 30 minutes and then tell something about his research interest about the simulations. Yeah. Thank you.
Thank you very much, Professor Dixit. Dear colleagues, it's a great pleasure to represent here some results of the collaborative work with Indian Institute of Technology, Guwahati. The subject of the presentation, research onto the material flow during the closed die forging with the help of numerical simulation. And today, and one more question, do you see the presentation slides now?
Yes.
Yeah, okay, perfect. So we talked today about the combined processes of metal forging, and we tried to observe in details two of them. These are isosomal forging and forging with torsion. We tried to compare these two processes and marked out some similarities, and that's more important, that differentiate these processes. And I will try to allow the specific of these processes, which is very important to take into account during the numerical simulation of them. So couple words about the combined processes of metal forging. These type of processes are very popular for the past decade, and the major characteristic of them that within the deformation zone there are some material flow, some direction of material flow, and material flow during plastic deformation try to flow in radial or transverse or forward or backward direction. From one side, it's a very complex material flow, which very difficult to predict. On the other hand, it's very useful to combine several forging operations in one tool and further produce a very complex part with complex shape. Some examples of such parts, but it's not the only this one. It's only the example which could be produced with the help of application of combined processes. Basic characteristic of them that parts needs minimum machining just after the forging. Some more examples based on the comparison of the processes which we discussed about during the presentation today. Isosomal near-net shape forging, and one of the typical part is a piston for automotive. The second process is forging with torsion, which much more applicable for the forging of axisymmetrical parts only, and this is the limitation of this process. Only a round shape, only axisymmetric part without any elongation elements. Then a couple of words about isosomal forging. The specific of this process that during the forging and within the deformation zone, it needs to keep the temperature constantly constant based on the initial values. Then the temperature of tools should be also keeps within the working stroke constant and equal to the initial temperature of the workpiece. On the other hand, it allows to get the low deformation load. Provide this approach to the construction of the forging process allows to increase the plasticity of materials, and from the practical point of view, it allows to get parts with the minimum percentage of surfaces which needs further material treatment. Based on these advantages of the process, it's understandable that some limitations and some difficulties characterize these processes, and much more accurate simulation should be performed. A much more accurate characteristic of material properties should be prepared just before the simulation performed. Some example of the part which could be produced with the help of isosomal forging is present on the screen, and this example is a very bright illustration of that the part has a large percentage of the unworkable surfaces. So this part produced following the principle forging and further used. Much more examples about the parts which could be produced with the help of isosomal forging is present on the screen. It's an elongated shaped parts. It's the parts with the ribs, thin walls, and round shaped parts. Typical problem which happened during the isosomal forging are linked to the first risk of defect appearance due to the complex material flow within the deformation zone. It's a characteristic of basic or major characteristic of isosomal forging. In contrast, if we will talk about forging with torsion, there is the less risk of defect formation, but if we compare the type of defects, it will be seen that almost the same defects could be follow the forging with torsion, except one of them, buckling. Buckling, it's not characterized, is not the typical defect which could be appear during the forging with torsion. That's why the explanation of that, it's very obvious. As we apply forging with torsion for the forging of axisymmetrical parts, so initially we choose the workpiece with definite initial ratio between the height and diameter. This ratio should be equal to 2 or 2.5, not more, but maybe less. So the probability of buckling appearance during forging with torsion is very, very low. On the same time, during the isosomal forging, the complexity of the forged part is very huge. And during and within the deformation zone, the buckling could be appeared during the, for instance, backward material flow, when the material get in contact with the upper tool, and then material starts to flow in the same direction as the upper tool goes. And on that stage, the probability of appearance of buckling is very high. And the manipulation with material deformed could be performed and could be estimated due to the research on the geometrical effect, the geometry of the forged part formation on this stage. Within the cooperation with Indian Institute of Technology, Guwahati, was developed the material model, was developed the model, fine element model of heat generation during the forging with torsion. Some aspects of this model, some approaches of this model are shown on the present slide. the model took into account several heat effects and much more very important for the forging with torsion that the driver of this process is linked to not only a heat effect due to plastic deformation, but also the heat effect, heat release during the shear deformation within the very thin contact layer. As it will be seen further, the heat effect during the shear deformation within the working stroke of forging with torsion 2 or 3 times more than heat effect due to plastic deformation. Several slides illustrates the simulation of typical defects which follows isosomal forging, and we talked about the nature of this effect and the parameters which follows and which are responsible for this effect appearance. Couple words about the structure of the typical CAE system, which commonly used for material flow simulation within the metal forming processes are presented on the screen. There is no anything extraordinary you can see, but I would like to pay attention only to one very important stage within the initial data collection and design. I mean the material model design. Based on our research activities, it would be made out that the type of material model, the number of parameters which pay in mind, which take into account the material model, has the great influence on the results of material simulation. Regarding to isosomal forging process scheme, the application of computer simulation take place when we talk about the design of operation of isosomal forging. As the isosomal forging performed at the elevated temperature, we are not able to use any flow stress model. We apply for the simulation only model which based on the flow theory approach, for instance, and this model should take into account the influence on flow stress, such parameters as temperature, strain rate, or maybe the evolution of microstructure. For instance, for our simulation, we used approach which take into account the combination of some mechanical parameters. The basic scheme of this model is presented on the slide. Within this approach, the problem which should be solved on the basis of experimental test, on experiments, is the identification of the coefficient of this model. Then, when we talk about the construction of the simulation, and bear in mind that the material model is identified, we should take and we took into account that any CAE system has some similarity inside the processor, finite element processor, which is linked to that material model has a limitation minimum and maximum for temperature, strain rate, and strain. This limitation goes from the experiments which used for identification of the parameters of the model. So any CAE system switch on the extrapolation or interpolation procedure when the governing equation within the finite element code is solved. If we took into account this limitation and if we took into our model that there is such limitation within the finite element code, we could increase the accuracy of the finite element simulation prediction and took much more effects which follows plastic deformation within the deformation zone. On the next step to prediction of, for instance, defects which follows or may follows the, for instance, isosomal forging. One of these defects is LEP. It's a typical defect which follows isosomal forging, or if to generalize the complex material flow within the deformation zone. And this study case illustrates which parameters could affect on the lab formation. For instance, some group of parameters connected to geometry of the part. So it was marked out 7 parameters. And as it was investigated and resulted, combination of the numerical values of these parameters could, for instance, reduce the lap length on the flange part of the forging, which was shown on the previous slide. The increase in radius allows to reduce the lap length twice. Then another parameter which also affect on the lap formation is rough draft height, which allows to reduce deformation load and also allows to manipulate with the lap length. If we goes to the thermomechanical parameters, one of the efficient parameters is temperature of the workpiece, but these parameters could not be varied within the wide range of values due to the limitation of the nature of material which is deformed. Then I would like to illustrate the finite element. I would like to illustrate the finite element model, which were suggested to forging with torsion. This model, firstly, were constructed and verified with the help of finite element code, and further validated on the basis of experimental results. Conditionally, forging with torsion divided into 2 stages. In reality, of course, there is only one working stroke within which the process carried out. Conditionally, on the first stage, the common asymmetrical upsetting is performed. The value of upsetting is of not more than 30% of the initial height. And just after that, the rotational moment is applied to the workpiece, and workpiece continues to deform along to the longitudinal axis, and within this second conditionally stroke, the rotational moment effect on the workpiece, and due to shear stress, shear deformation, the diameter of the workpiece increases while the height of the workpiece decreases. Such kinematic of the material flow follows the very huge release of heat on the thin layer of material which is close to the contact surface. Due to that, and as the result, the increase in temperature could be up to 200 degrees if we talk about the plastic deformation of aluminum alloys. And let's compare the increase in temperature due to heat effect of plastic deformation during the first stage is not more than 40 degrees of centigrade. But during the second stage, the temperature could increase up to roughly 200 degrees. Experimentally, we proved this increase in temperature, and for the experimental test within the collaborative project with Indian Institute of Technology, Guwahati, was designed a special test ring, which allows to control the temperature rise within the deformation zone online. So the thermocouple installed within the deformed material in several points, and during the deformation, the data driven to the computer and then treated in the definite within the definite algorithm, and the value identified the temperature rise visualized on the special program. So this, I think that is the first step to the research onto the nature of the specific of forging with torsion processes, and I do hope that within the cooperation with Institute of Technology Guwahati and personally with Professor Dixit, we get advance in the investigation of this process, and some very interesting results could be appeared in the nearest future. Thank you for your attention. If you have any question, please ask them.
Any question from participants, attendees? I think that they can write in chat if they want. You can put a question. Yes.
We request the audience to post their question in the chat box.
I think they can write in chat box now only. Yeah.
Yes, sir.
Yeah. Before that, one participant is here. He can ask with this one. He was listening. Okay. Yeah. Yeah. Come. This one. Okay.
Good afternoon, sir.
Good afternoon, sir.
Sir, just one fundamental question regarding the defects that you have mentioned in one slide in forging process. I just want to know that the defects you mentioned in some slide 2 or 3 like that.
Do you mean the slide where the comparison between the
first or second slide in the beginning, sir?
Beginning.
Okay. This one.
That one.
This.
Yeah.
Like
Okay.
also on the. Sir, can you please I suppose can you please repeat like the defects like this lab defects, or how it can be eliminated? Can you say please repeat? I missed it while you were presenting. Like the process, how it can be eliminated, this lab defect.
Do you mean the first one? Yeah.
Yes, sir.
The lab defect. Due to the complex material flow within the deformation zone, the lab defect is very common within and appropriate for isothermal forging. For instance, let's see, for instance, this part of irregular shape, and here you can see the lab formation on the inner surface of the part, which is in contact with the upper tool. And this lap forms when the material starts to flow in the element of a regular shape, which allocated here. As only one example. Then further, just a moment.
Yeah, this one.
Yeah.
This one. So there is no, here there is no lab that there is a flow through defect. And this line, the curvature of the line allow to visualize how the flow through defect is allocated. So of course, it's possible to interpret the flows through defect as the inner lap which goes inside the material from the surface. When there is no any freedom for the material flow, the material and there is a big difference between the velocity of material allocated in the central part and the velocity of material which is flow along the surface of the tool. And the curvature of the Lagrangian line illustrates the intensive material flow. In these points, material keeps his position, but in this part, the material continue to flow and fill the tool surface.
Okay. Yeah. Okay. Yes. Any other question that from anyone? Okay. I think. Okay. Yeah. Okay. I think Professor Pavel, maybe after we should also see the what happens to microstructure, etc. in simulation. Do you think that this may be our future task when we are doing deformation? What happens to grains and microstructure and mechanical properties of the product? So what is means your opinion that in simulation it can also be probably done with the help of this one, because once we know the temperature, we can understand that how the heat treatment takes place. So any comment?
Yeah, within our project, we had the look to the investigation of material structure. Yes. And forging with torsion, the specific of this process is that the major influence on the plastic deformation has or is connected to the shear deformation. And the shear deformation in this case is equivalent to the severe plastic deformation. So during the forging with torsion is able to achieve a very higher level of the material deformation. Yes. As a result, the microstructure change many times during the rotation of the parts of the workpiece. And it was my mistake. I needed to include into the presentation the examples of the microstructure. It's very interesting to observe the microstructure obtained just after the forging with torsion. It's similar to the sand which fill in the cup. there is very small grains of a regular shape. It's very difficult to identify the size of this grain due to very small size of them. And we tried to use electronic microscopy to identify accurate value of the average size of grains. And we failed in this. Due to that, the distribution of the grain size very different from one point of the workpiece to another point. And the size, absolute size of the grain is very small. And probably new approach for the identification of size of micrograins, grains on the which are located along the boundaries, could be developed in the future.
Okay. Thank you very much. So yeah, so if there are no questions, then I think Professor Ramesh Babu, you can thank him and yeah.
So we feel honored and privileged to propose a vote of thanks on this session. We take this opportunity to express our sincere thanks to today's keynote speaker, Dr. Pavel Petro, for providing insight the technology of modern trend in material forming. Dr. Paul Petro indicated isothermal forging and forging with torsion. Also, he talked about computational modeling, highlighting the formation and elimination of defects. And we express our deep gratitude to Dr. Dixit handling the session. At this end, we thank everyone for your cooperation and support. Thank you.
Thank you. Okay. Thank you very much. Okay. Fine.
Thank you very much.
Yeah. Okay. Fine. Yes.
Thank you.
Yes.
Thank you, colleagues.
So we can review the meeting, I think, now. No? Okay,
Yes, sir.
fine.
Yes, sir.
Fine. Okay, good. Okay.
Thank you very much for invitation.
Thank you.
Yeah, we can announce.
The delegate announcement. The delegates are kindly request to join the technical session 1. Will begin at 2:20 p.m.